So what I want to kind of preface this is in just saying that if anybody has any questions, um, just let me know. And what my plan is to go through this PowerPoint that I have, and when we get to the end of the PowerPoint, I'll call for questions, and then hopefully we can have some discussion. I really do hope that you all have some questions, and we can have some dialogue, and then after that, depending on how much time is left, this is about a 15-20 minute presentation as far as the PowerPoint. I plan on going into Zmax, kind of cracking open one of the transmission sphere designs that I have, and then showing the cost estimator tool that we just implemented inside of Zmax. And we can have a little bit of a Q&A on how to use that tool. I know one thing that I'm sure you might have in classes is you have an optical design and then you want to figure out how much it costs. And so the cost estimator tool is a really nice, convenient way to figure out ballpark how much your design would cost if you can actually use the cost estimator. If you can figure out the little box that I made to get you a quote. So with that said, I'll go ahead and get started. So this is important considerations when designing optics for manufacturability. My name is Kenny Rains, work at LaCroix Precision Optics. I've been here for about 5 years now. So who is LaCroix? We are essentially an optics manufacturer. We manufacture spherical lenses, A-spheres, achromats, prisms, windows, wedges, mirrors, and we do our own coatings. We work with optical glass, fused silica, filter glass specifically. So we also tend to work in a size range from 4 millimeters to 150 millimeters. Just in general, you'll find that optics manufacturers tend to specialize either in micro optics. So think 3-4 millimeters or smaller, this kind of mid-range, which is where LaCroix is at. And then you'll find some vendors that just specialize in large optics, 150, 300. You guys specifically have an incredible telescope lab where you make mega optics. I don't even know what you would call those. I got to go tour there once. It was incredible. So, and a typical lead time you'll run into, and this isn't just LaCroix, but 8 to 10 weeks for a standard delivery, and with options to go to 2 to 6 weeks expedited deliveries. And we work kind of a niche of LaCroix is being able to go from prototype to production in the same facility. So we can make prototypes, onesie, twosies, all the way into thousands and tens of thousands. We have some optics we make hundreds of thousands of. So LaCroix has been in business for over 70 years. This is third generation leading the company at this point. Started out in Chicago and ended up moving to Arkansas due to two brothers who commuted from Arkansas to Chicago to work. And the wives ended up saying, you can either have your jobs or have us. They came back to Arkansas and set up a remote facility. And then LaCroix ended up moving down about a little over 40 years ago to Batesville. And talked a little bit already about what makes us different. And so with all that said, let's get into the actual movement from prototype to production. So you start out with a concept, and whether it's figuring out what an initial problem is, and you're working inside of Zmax and you're making your prototype optics. And then finally, you want to actually get some glass made. You want to see if the thing will really work in reality. And finally, how do you scale to production? And so it's really important to communicate with your vendor. One of the biggest issues that I find, my job specifically, is I work with optical engineers, people like yourselves will become once you graduate school, and I help you figure out, can we make it? How do we make it? How much should it cost? And so one of the biggest issues I run into, though, is I wouldn't say most of the time, but a lot of times people underspecify the tolerances. So they'll just send me like a drawing and there's no tolerances on it. And then I kind of have to fill in the blanks because we both have to agree on what we're going to make. And you're never going to have something made exactly to what you design inside of Zmax or whatever optical design software that you use. And so you've got to have some flexibility with your vendor. We've got a tolerance chart that you can download on our website. And I think we're going to try to send over a package, especially if you all are in Tucson, over to U of A. And that way you all can have our nice laminated tolerance charts for use in the future. And, you also want to specify what all you want with your optics. So for instance, some people require inspection data. Like even on my little transmission sphere project I'm working on, I wanted inspection data so that way I could come back, get what the lenses were actually manufactured to. I was going to go back into ZMAX, put all that stuff in there, and then re-optimize my spacing based off of what was produced before we ever started cutting the mechanical housing. And do you want coating graphs to see what the actual coating performance is? You want material certification, so that way you can see, we call that also melt data. So you can see what the actual index and dispersion values are on the melt of glass that you have. And then these things called first article inspection reports. Basically, that is just going line by line through your print, and we document every single thing that's on your print. And also a good thing to specify is what lead time you're looking for. That's something that I've had people that say that they wanted it yesterday. We're still working on the flux capacitor on the time machine, so we don't have that installed yet. We can't do that yet. But if you do let us know that there's a certain deadline for getting the quote or getting the optics, we'll try our best to help you out. So I joke around with people that there's 3 kinds of services that you can get. You can get good, cheap, or fast, but you only get 2 of the 3. And so you can either get good and cheap and it won't be fast, fast and good and it won't be cheap, cheap and fast and it won't be good. Now we try to do all 3, but it kind of comes into, if you want something that's really tightly toleranced and you need it in 3-4 weeks, you're going to pay a premium for that. Versus if you can wait for us to get like molded blanks, there's 2 different types of blanks, and I'll get into this in a minute. One's cheaper than the other, but you can get one faster than the other. And so just kind of letting us know up front what you're looking for, and we'll try to present the best package we can for you. For the most part, you will find that optics manufacturers can make the optics 4 to 5 weeks after receiving material. So for single elements, we can typically have a 6 to 8 week lead time. Acromats, you kind of tack on another week to that. Same thing with triplets, takes a little bit more time to put everything together. And so 7 to 9 weeks on those. And if we have material in-house or I can get it in a week or 2, you can kind of trim some time off of that lead time. Can you all see, are you seeing everybody's camera? Can you see my whole screen? Can you see this little blank picture?
We just see the slides.
Okay, cool. It's a little bit cut off on mine, but I just wanted to make sure that everybody could see this. So in this little drawing that I have, we're a subtractive manufacturing process. And so we have to start out a little bit bigger than the part that you want, which that's kind of important because I know like in ZMAX, you can specify what edge thickness you want. And edge thickness is a really, really critical thing because we have to have something to grab onto. So if you specify that you want like a 1 millimeter edge thickness, it still may be problematic for us because we've got to go 2 millimeters over in diameter versus what you want. And this is there. All of these things that I say are general rules. They can be broken, but we're going to make it a little bit bigger in diameter and a little bit thicker. So that's something to think about. If you have a lens that has no edge thickness at what you want, then it's going to have probably most likely even less at what we would call processing diameter. Next thing would be cut versus molded blanks. I actually just got done working up a quote where, I was able to shave off of an SLAH 66 blank went from $70 each down to $3 a piece, just going from molded to cut disc blanks. And if you think about what a cut disc blank is you get these big pieces of strip glass from Schott or O'Hara, and you literally are core drilling out. So think of like circle packing, like soda cans inside of a rectangular case. You'll never get 100% yield on that. So you pay for that. Versus molded blanks, you get almost 100% yield, but not all materials can be molded. Like fused silica, for instance, can't be molded. It's always a cut disc blank. So just remember that cut disc blanks, you can tend to get really quickly. Virtually all materials are available in cut disc form. Versus molded, you can get it at a much lower cost, but it takes a lot longer to get it. The molded blanks that I just got a quote for, they were dirt cheap, but it was going to take me 10 weeks just to receive raw material. So you tack on 4 weeks past that, you're looking at almost 3.5, 4 months before you get optics, versus I offered him a solution using cut dish blanks of 6 weeks, but it was much more expensive. And so, you got to kind of weigh those trade-offs and jokingly, which two of the three do you want? So we'll walk through a process of manufacturing an A-sphere. I've got some shop footage that I'll share with you all, but essentially you start out, you grind and polish the outside surface of the lens. So surface 1, surface 2, then you come back and you'll clean it up, get all the cerium oxide or polishing compound off of the optic, center it, aligning the optical and mechanical axis together. You clean it again and get the oil off of that process. You inspect it. You verify the center thickness, diameter, the surface quality, all the different specifications of the optic. Finally, you coat it, check the coating, go to a final inspection. Essentially, anytime you inspect it, you check the surface quality, because the surface quality can be damaged at any time somebody's handling the optic. So with that said, can everybody hear this? Can't hear it?
Or it's really quiet.
Really quiet. Let me see. Still quiet?
Yeah, I think it's just going through like your mic, like it's not playing through the computer, if that makes sense.
It does make sense. Okay. Is that any better? Or can you not hear it at all now?
No, not at all.
Okay. Well, dang, that's too bad.
Just a heads up, when you go to share on Zoom, there's actually an option to share your sound as well as your screen.
Okay.
So if you go ahead and reshare, you can stop the share and start again. Towards the bottom of the sharing window, there's actually a button you can check to choose to share your sound as well.
Okay. Apologize for struggling on this.
All good. It's expected.
Yeah, for some reason it's only showing me the faces of everybody. I'm not getting any other menus from the Zoom. Well, I'll skip the video for now, but essentially it's just grinding and polishing. This is the polishing process, the metrology. I'm assuming that everybody has seen optics manufacturing before. If you haven't, let me know. Pretty much everybody has, I guess, has been down the lab and seen grinding and polishing. So it's not going to be the most heartbreaking thing if we skip that. You can go to our website and we have a lot of videos showing grinding and polishing. So anyway, I'll hop back into this PowerPoint. So then you've got your coating, and ultimately you can specify if you want an anti-reflective coating, if you want a broadband or a V coat. Broadband would be for like if you had a camera application and or a rifle scope and you wanted to get 400 to 700 as low in reflection as you could, that would be a broadband BBAR. Versus like on my little transmission sphere project I was working on, I'm trying to minimize reflection at 633, except for on the reference sphere surface. And so that would be what's called a V coat. It's just a single wavelength that I'm concerned with. And so you can get a lower reflection on a V coat than you can on a broadband. Then you also have reflectors and beam splitters, filter coatings. Hydrophobic coatings are common on rifle scopes. And then finally, environmental testing. If you're familiar with mil-spec testing, testing humidity and abrasion, adhesion. How well does the coating stick? How well does it deal with salt spray and just different environmental factors that the lenses may run into? You can also specify those tests, and anybody that does coatings will pretty much have equipment to be able to do those tests and give you the results. And so your next step would be, if you've made the prototypes, how do you scale into production? And so this is when you try to optimize for tooling, making sure, like on this specific lens that we're looking at, it's a convex plano spherical lens. And so on the plano side, I can get a lot of lenses per tool, so that lowers cost. On the convex side, I can make what's called a spot tool. It's where you put multiple lenses on a tool and run them all like one big lens. So that lowers cost. You try to switch to molded blanks, and hopefully you can afford the lead time and just kind of get things worked out in volume such that you can, start taking deliveries every month. And as you're doing assemblies, you're getting your optics in and trying to optimize that flow with batch sizes. How many can you get in a coating run, for instance? And, we work with you on all these steps, or if you went to any other optics manufacturer, I'm sure that they would work with you as well on that. So just kind of in summary of this presentation, communication is key. Talking to whoever the engineer is or whoever your rep is for your optics, letting them know up front what you need, asking for manufacturability feedback. Quite a few times I'll get these lenses that are literally unmakeable, like just physically, at least with grinding and polishing, are unmanufacturable. Whether it's sometimes they show up with a step on a convex radius, and if you think about a full aperture grinding and polishing process, you have to literally go off the edge of the optic, and so a step on a convex just isn't physically possible. Now you can cut into it and get a step that way, but another process like molding, you can get that. So it's important just to talk to whoever you're getting optics from and see what they can and can't do, and figure out is quality, cost, time. What are the critical aspects of your project, and start with the end in mind. Where do you want to end up with your project? And with that said, thank you for your time. And do you all have any questions on this presentation, or just in general about optics?
This is a very not specific question, or specific to the slides. I'm just curious. So did you start your career in optics, or did you find optics somewhere along the way?
No, I took all of 2 weeks in optics and physics back in college. I actually studied electrical engineering and got my master's in engineering management. And played football for 5 years at Arkansas State University, not the ASU near you guys, the ASU up here in the South. So no, I actually went initially to work at a lawnmower manufacturer here in Batesville, Arkansas, and did that for about a year. Really enjoyed working with metal, did not enjoy the people that I worked for, and so left there after a year and came over to LaCroix and have loved it. I've really loved the optics, and just the community in general is great. The people in optics they're awesome. It really is a great industry to get into, whether you're on the designing side, on the manufacturing side. It's top-notch people.
Thank you.
Yeah, one other thing I'll add too is I don't think there's too many industries, at least that I could be involved in Arkansas and have my hands in so many different groundbreaking technologies. I work with cutting edge companies and with space optics, with defense, with medical. I've got a customer over in California who makes, life-saving medical devices that we put optics into. I've got one that we're literally putting optics into satellites and shooting them into space. So I get to dabble in all of these different fields, all from Arkansas, which is the place that I've grown up and loved. So really do enjoy being able to get a taste of all those different industries and be a part of them.
I have a question.
Uh-huh.
Say I were to order some A spheres from LaCroix. Uh, After the manufacturing, how do you guys measure the A spheres? Like, would I get like a 2D map, a 3D map?
That's a great question, Henry. We actually have a white paper on 2D versus 3D metrology. So industry standard would be a profilometer trace. And that's just literally a 2D trace across the surface of the lens, which is just a sliver. Um, you know, that's what's standard. You can request 3D data. Like we have a 3D measuring device for A spheres. And so we can provide that. And I would say just from what I've seen, if I had a really critical design, I'd probably want to see at least one 3D trace because a profilometer trace, if you don't at least do like one at 0 and 90 degrees, you can miss out on some pretty serious asymmetry. And that's something really that only 3D or multiple traces is going to find.
I have a follow-up question. I did read that white paper. Um, so let's say I were to get a batch of A spheres from LaCroix, and how many how many would you recommend I get the 3D measurement of, just because one might not be representative of the whole batch? I don't know if one is representative of the whole batch, but I don't, in like less, I don't know, in a mechanical engineering environment, you get like what, 1 out of every 13 or something. And that's just for pretty generous tolerances.
Right. So you have what's called AQL levels. I'm not too terribly familiar with it. That tends to be more of like the quality side of engineering, but uh, it depends on how critical the application is. It's something to where if you requested 100% of them be 3D traced and be serialized so that way you have the 3D measurement to the part, we do that. It just, you pay more money. You may pay $10, $20 per 3D measurement, somewhere in there, which, if you're spending $1,000 per part, that's not very much. Or if you were trying to really lower your budget, you may try to do some sort of AQL level, and maybe you get 1 out of every 10. But it's not uncommon at all to have the A sphere serialized and at a minimum provide profilometer traces for each A sphere. That's not uncommon.
So that's everything I wanted to know.
Awesome. Thanks, Henry. Anybody else have any questions?
Yeah, I have a question. Oh, you go ahead.
All right. So I know you mentioned edge thickness and tolerance is missing. Do you see any other typical thing missing for an optical part coming in, or like, just common mistakes when somebody's defining a part?
Yeah. I think some of the most common things that I see missed would be somebody not putting like the surface quality that they need. What else? So if you pick up one of those tolerance charts, you can download the free PDF. As long as you're kind of at least putting something for each one of those: center thickness, diameter, centration, optical power, irregularity, surface quality, and you have all those constrained. Do you want bevels or not on it? That's pretty much going to cover everything. I do have some videos coming out in the future where I just go through and go into ZMAX and show how to make an ISO 10110 print that you can send out. Because I've been surprised at how many people will just send me a ZMAX design and then be like, can you make me a print? It's like, sure, I can make you a print. That's not an issue, but not everybody does that. Like even at LaCroix, I'm the only person who knows how to use ZMAX. So you'll probably run into a lot more optics manufacturers that don't have ZMAX. So you need to actually provide them a print. I would say if you have a print and you have tolerances, you're ahead of the game compared to most of the people that I deal with.
Sounds good. Thank you.
Yeah, no problem, Hayden. Thank you for the question. I believe there was one other question.
Yeah, mine's more of a general question too. You said that you kind of worked on a huge variety of different types of projects.
Uh-huh.
I was just curious as to what one of your favorite one was, or one you found really interesting or something along those lines.
Yeah. So there's some that I can't talk about because of NDAs. Then there's others that I can. So let me give you one that I can. There's a company called Phoenix Technologies over in California, and they make a retinal imaging device. And I actually got to go there in person to their facility and see the device and kind of help them troubleshoot the optics. They're really struggling because they essentially had 3 optical surfaces that they focus on in the imaging. And so if there's a scratch or a dig on one of those surfaces, the doctor could think that that's on your eyeball. And so what they end up doing with this device, so, is they scan the eyes of newborn children, and they can tell if their eyes are properly developing or not by the blood flow in the eye. And so if it's not, they can go in and do a surgery and save their vision before they lose it, which, I've got an 8-month-old son, and he can't tell me what he can and can't see. I think he sees pretty well because his little head follows me all around the living room whenever I'm walking around there. But I think it's awesome that we're a part of, helping save people's vision and helping people and it's all around the world. They use these things in the US, they use them in China and Russia, even in the Middle East. I mean, they sell these instruments everywhere. So I think that that's a really cool project. Another one, there's several I really like. Another one is laser optics. So I've got a customer in Michigan that makes high power laser cutting optics. So I built a CNC plasma cutter for fun for business I had on the side. And so cutting metal is something I really enjoy, and being able to cut it with lasers is a little bit cooler than a plasma torch.
Yeah, those sound really awesome. Thank you for sharing.
Yeah, no problem. Anybody have any other questions?
Hi, this is John. I got a question about the subtractive aspect of the manufacturing process.
Sure.
In the spirit of getting as many of the 3 legs of that process of, cheap, fast, and high quality, there's typically an effort to reduce the tolerances, open the tolerance as much as possible. And my question is, in doing that, since it's a subtractive process, my understanding and assumption is that you're going to remove material only up until the point you get within that tolerance zone.
Yes, that is true.
And do you have any recommendations, since that would be kind of I think ZMax and your normal tolerance analysis kind of assumes a normal distribution around the center of your tolerance, but that's
right.
Probably not what happens in reality. Do you have a suggestion on how to deal with that?
Yes, I've got a customer that designs rifle scopes, and they've been trying for a while, like how to model that. So let me just tell you some of the tolerances that we shoot for nominal, and some of the tolerances we just try to, as soon as you get in, you're done. So radius, for instance, you're typically going to shoot for nominal on radius, unless you have some sort of a test glass. Like if it's a really flat convex radius and you have a test glass, you may try to shoot for that. But most of the time you're shooting for the nominal radius. Whereas center thickness, if you're 10 millimeters plus or minus 100 microns, whenever you're grinding and polishing, like whenever you polish that in and you're 10.9, 10.95, you're done. You pretty much would stop at that point. And the reason why is because if you have to repair that optic for surface quality or for optical power regularity, center thickness is one of those things that tells you how many opportunities you have to try to fix the optic. And so you would try to stop on the high side of the tolerance. And so what's interesting though, is you'll find those optics typically grouped very closely together at the top side of the tolerance. You may specify plus or minus 100 microns, but you may get them all and they're plus or minus 10 microns to the top side of the tolerance. And so how you would model that, I don't really know. But Same thing with diameter. You would pretty much shoot for the high side. Versus like centration, you try to get that to 0. Our people are going to try their best to get that to 0, no matter what. If you specified 10 minutes, they're still going to try to make them perfect. And so mainly it's that center thickness and diameter to where they're trying to just get into the high side, and then that's where they would stop.
Okay, great, thanks. Is your rifle scope customer, was there issue that their predictions weren't meeting the reality because of this issue, or was that unrelated?
It was just, he's a guy that's trying to always get like I told you, whenever we first started, I'm sitting here trying to tinker with this transmission sphere, and I can always get it a little bit better. And so that's kind of how he is. Like, he's always like mad scientist trying to get it a little bit better and a little bit better. And so he's like, well, my simulations, I'm shooting for nominal and the distribution's around nominal. And so then he ended up writing some custom macros that like shifted the distribution around the high side of the center thickness. And he was able to get a more accurate representation of what he was actually getting from us.
Yeah, that's very cool. I'd imagine that would be something that's, obviously very common, since this is how most optics are manufactured. And that would be something that maybe ZMAX or one of the other codes would be interested in eventually incorporating into their, production software, since that would probably be appropriate for most people.
I think it would be something good for them to develop, if you could just pick like high side, low side, whatever it is, and then that's where the distribution is around. Because it's common. It's very common, because if you ever go under on center thickness, I can't just like glue glass back to the top and rework it. So versus on radius, if I'm a little bit under or over, I can tweak that as long as I have thickness. So, which that's also a huge cost driver, would be if you really tighten down center thickness and keep everything else really tight, your cost really starts to go up.
Yeah, like thinking about that, and the number of tries you get, that's kind of a practical way to consider that.
It
Thanks.
is. Yeah, no problem. Like once you get under plus or minus 30 microns of center thickness tolerance, you start to lose almost any opportunities. Rough rule of thumb, you may take off 10 to 30 microns per attempt at trying to hit all your tolerances, depending on if you have to regrind or if you can just repolish. So like for LaCroix, a preferred center thickness tolerance would be plus or minus 0.1 millimeters, possible, and really not that much of a price increase, plus or minus 0.05 millimeters. And then about the tightest we tend to do is plus or minus 0.025 or plus or minus 0.03. So 25 to 30 micron tolerance.
Right. So your preferred tolerance represents like 3 tries, roughly.
Yeah, pretty much.
Cool.
And most of the time they'll come in on the first shot, no matter what the tolerance is. But if you have a 100-piece order and 90% of them come in, well, we got to fix the other 10. And so then we'll go back and repair those. And so that's fairly common. Precision optics is not it's not easy. It's a lot different than like the metal manufacturing that I was doing before this.
Yeah, I bet. Thanks again.
Yeah, no problem. I guess, do you all want to look at ZMAX and kind of see that cost estimator tool? Okay. Yeah, let me hop over into that. Okay. So can everybody still see this? Do you see 3 lenses?
We just see the slide. Yeah.
Still see the slide? Uh-oh.
I think it's when you share the screen, you pick which screen you're sharing.
Okay.
Up there.
Yeah, there we go. So this is basically it's a 2-inch 3.3 transmission sphere design. And I made it 2 inches just because I've got some glass laying around in house that I could just grab some blanks and make it. This is more of a test of if I even know what the heck I'm doing in optical design, which I don't know. So I'm trying to learn. If anybody's designed a transmission sphere, let me know. I would love some advice. Has anybody actually designed one of these, maybe for like a class or something?
Yeah, I've designed one for a class before.
Cool.
But we didn't have to make it. It was just modeling a transmission sphere that we already had in the lab.
Yeah.
So,
What F number was it?
I think it was F3.5, something like that.
Okay.
Yeah.
Cool. Well, so long story short, this is the design I ended up settling on. I've made a mechanical housing for it, and I think it's makeable. So long story short, I made some ISO 10110 drawings for it. And so to use the cost estimator tool, what you do is right here in System Explorer, cost estimator, manage providers. There's only 2 providers that do the cost estimating at the moment. There's Optimax and there's LaCroix. And so you just hit open browser and it'll take you to our website, and you apply for the cost estimator tool. We approve you, you get a username and password, you put that in here, and just go ahead and save it. And so then you make your ISO 10110 drawing, and you've kind of got to tweak it so that you can get a cost estimate. So whenever I was originally designing this whole cost estimator tool, I make a box. If your print or your optic falls inside the box, you get a quote. If it doesn't, you don't get a quote. You get an error code. So in this one, I've set it up so that I'll actually get a quote. And I worked on a quote internally. I was within about 10%. So it's fairly close to what you'll get in reality, with a huge asterisk. I would say it's good for like rough order of magnitude. Don't think that this is like an Amazon price that you can buy and get in 2 days. So with that said, this is the pricing. We quote from 1 to 10 pieces. So you get 1, 2, 3, 4, 5, and 10 pieces. At LaCroix, you see a pretty big price discount whenever you get to 25 and 100 plus pieces in your per unit pricing. This is also per unit. Just want to make that clear. But you can see like the total cost to make 2 is almost the same as 1. So we very rarely make just 1 piece. It's almost always like for a couple $100 more, you can get 2. And so it's almost always worth it to make at least 2, because we're going to start to make 1. We're going to start anywhere from 6 to 10 blanks. So and that's just optics in general. You have a pretty high loss, whenever you grind it, somebody might keep a piece of glass there. Then whenever you polish it, somebody keeps a setup piece there. And so they keep these setup pieces throughout. So you need to start several more. And then there's minimum orders for material. Long story short, it normally makes sense to order more than 1, at least 2. So this is my price. Has anybody used the ISO 10110 tool inside of ZMAX to make a print? Would you like me to show you how to do that?
That'd be awesome.
Okay. So what you basically do is you come over to Tolerances, ISO Element Drawing, click on it. It always starts you out with just this random surface. So then you come in, and I'm going to just choose surface 2 and change it to singlet. I put all my little information in here. Okay. And then you can go ahead and choose your cost estimator. I've chosen LaCroix. For the LaCroix one, it really doesn't matter what quantities you put in because it's only going to spit out 1, 2, 3, 4, 5, and 10. The Optimax one is a little bit different though. So then I'm going to come in and I'll reset from the lens data editor. And so it'll automatically fit in my radius, my clear aperture, my diameter. And So I'll go ahead and put in a diameter tolerance of plus or minus 15 microns. I wanted to hold it pretty tight, so that way it was pretty well trying to eliminate decenter whenever I put the optic into the barrel. 3 fringes of power, a quarter fringe of optical regularity. I'm going to do 30 seconds optical deviation. So for the centering error, or it's 4 in ISO, you got to specify in minutes. So I had 30 seconds for 30 arc seconds for the deviation on the print that I put for internal use, but I have to put 0.5, half a minute on this to actually get a quote. Then I come in here. The way the LaCroix one works is we are not able to really read ISO 10110 surface quality. And it's because we only work in mil spec surface quality. And so here's the main trick. So in other surface, the very first one, you put what mil spec surface quality you want. I'm going to also add a chamfer to this side. Doesn't affect the quote at all. I'm just doing it for the print. So long story short, the thing that people mess up on a lot with this tool is you put mil spec surface quality in the first little area in other surface located on left surface codes 5 through 6. Then for the material, I'm going to put plus or minus 50 microns on the center thickness. And for the index and dispersion, it's only quoting standard grade material. Standard grade would be plus or minus 3 zeros and a 5 on index, and then plus or minus anywhere from 0.5 to 0.8% dispersion. I'm just going to leave those alone for right now for what I'm doing. We have no way to read the stress birefringence, bubbles, or inhomogeneity. So if you specify, that's why I said huge asterisks on the quote. If you specify something crazy for the homogeneity, it is not an accurate number. It is only representative of standard grade material. So I'm going to reset from the LDE. The coding, LPO, LaCroix Precision Optics, broadband visible 458607. So this isn't like the matrix. It has a meaning. We have a ZMAX user guide, so you can actually see what all those letters and numbers mean. But the 458607, that's the index range. So BK7, which is what this glass is 1.517. So it falls in the middle here. What I really need for the coating is a V coat at 633. That's not an option inside of the software at this point. I know personally that the broadband visible is a pretty close cost to what the V coat would be. So at least for the cost estimator tool, it's close enough for what I'm trying to do. I'm going to go ahead and set this effective diameter to just 52 and change this to 3 quarter fringe irregular and 30 seconds on the centering error. Add a chamfer and then 60-40 on this side. There we go. We've got a print. The only thing I forgot is I didn't put a diameter tolerance on this side. Okay. And let's cross our fingers and hope we get a quote. There we go. So there's your quote. And that's the nice thing about using the quote this way. You can click this little cost estimator tool here and pull in your parts. I find it much easier just to click the tab down here. And for any nerds, what I'm actually doing is I'm taking this XML file and I'm kind of parsing it out in a Python code to get a mathematical description of what in the world the lens is. So that's how the program actually works. Anybody have any questions about making a print or using the cost estimator tool?
How much can you expect the cost to balloon if you're asking for non-standard material grades?
There is no way to guess. At that point, I would say if you're using non-standard, you need to just go ahead and get a quote. You could do this and get a ballpark, but it seriously can go up 10x, 100x. Just depends on what you're asking for. Homogeneity is a huge cost driver, because when you get into the really high grades, they literally have to polish each blank, measure it on an interferometer before we ever even get it. And so the lead time is really high, takes a long time. The cost is really high, but there's some applications that you have to have that. And so, if you need it, you need it, but you're not going to be able to use this tool and get an accurate representation. One other thing I do want to show y'all, this is really nice because you can come in here and tweak the tolerances, and we'll go ahead and tighten up the surface quality too and see what happens to the price. It'll go up, fair warning. But it's a really cool way to quickly find out a correlation between, so we went up, like on the 2-piece price, we went up almost $200 per piece. Now that may be worth it. You may even go to 10.5, or you may be like, well, I'm trying to stay under X amount of dollars. Let me loosen up this tolerance and this tolerance because they don't really matter. And so it's a cost estimator tool is a quick way to figure out what tolerances are driving the cost. And it's pretty close, but if you're going to actually intend on buying it, just go ahead and send us in the prints and we'll get you a firm quote. Any other questions? Okay. Well, I want to thank everybody for your time today. And if you ever need anything, my email is just kenny@lacroixoptics.com. Feel free to ask me any questions, even if you don't have a quote. If you just have a question in regards to anything, more than happy to talk with you. So, and also our phone number is on the website. So just ask for Kenny if you call in, and appreciate you all.
Okay, thank you so much for joining us. And thank you all for coming.
Thank you.
Thanks.
Thank you. It was great.
Thank you.